Welcome back, everybody. This is our first session in JEE Mains previous year questions for chapter Magnetism and Matter of class 12th. Before this video, in this series, we have made similar type of videos for various chapters, and all of those videos are available on our YouTube channel's playlist section. You can find all in the channel's playlist. We have also started similar series for NEET previous year, so videos related to that playlist are also available in the dedicated playlist. And if you find these videos useful, helpful, then do press the like button, share them as much as possible, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, let's start today's video. Here is the first question. So let's start. A small bar magnet is placed with its axis 30 degree with an external field of 0.06 Tesla, experiences a torque, and the magnet minimum work required to rotate it from the stable to the unstable. Now we have magnet, and axis of the magnet and magnetic field makes angle of 30 degree. So let's first draw a magnet. Suppose this is our magnet. This color is not good. Suppose this is our magnet, and this is the direction of magnetic dipole moment. Now it is mentioned this magnetic dipole moment makes an angle of 30 degree with the magnetic field. So magnetic field will be something like this. This will be the magnetic field. So this is B and this is magnetic dipole moment of the magnet. Now we know that torque for any magnet is given by M cross B, and as mentioned that angle between these two is 30 degree here. So, and value of torque is also mentioned, that is 18 into 10 raised to power minus 3 equals to M, that we will find cross B. B is 6 into 10 raised to power minus 2 into sine of 30, and sine 30 is half. So this will give us 3 and this will give us 6 here. So 6 divided by 6 into 10 raised to power minus 3 divided by 10 raised to power minus 2, or it will be 6 into 10 raised to power minus 1 is equal to M. That's the value of magnetic dipole moment. Now we have to find out minimum amount of work required to rotate it to the stable equilibrium. Rotate it from the stable to the unstable. So we have to find out the work from stable to the unstable. Now for stable condition, we know for stable condition theta is 0 degree, and for unstable condition theta is 180 degree. So energy, or we can say potential energy, in case of stable condition, suppose that is initial potential energy in case of stable condition, that is M negative of MB cos of 0, so it will be minus MB. And final, for the unstable condition, it will be minus MB cos of 180 degree, so it will be plus MB. Now we have to find out the work done. So work done, we know it is change in energy, or final minus initial, so MB minus of minus MB. So this will give us 2 MB, and that will be twice. Value of M is 6 into 10 raised to power minus 1, and value of B is 6 into 10 raised to power minus 2. So 36 into 272 into 10 raised to power minus 3, or 7.2 into 10 raised to power minus 2. That is option C for us. Now let's move to the next one. A circular coil has moment of inertia 0.8 kilogram per meter square around any diameter and carrying a current to produce magnetic field of 20 ampere meter square. Magnetic moment is given. The coil is kept initially in the vertical position. It can rotate freely with the horizontal diameter. When a uniform magnetic field of 4 Tesla is applied along the vertical, it starts rotating around the horizontal diameter. The speed of the coil acquired after rotating by 60 degrees. So we have to find out speed of the coil, and as we know that the first of all, let's draw a diagram for this uh, question, then we will be able to understand it better. So magnetic field is applied along the vertical, so we can say magnetic field is along y-axis. So let's draw axis. These are x, y, and this is z axis. Now here our magnetic field is in the vertical direction, so suppose this is the direction of the magnetic field, and now we need a coil. So let us suppose this is the coil we have, and these are its axes. This is parallel to z axis, this axis, and here this axis is parallel to y axis. And if you can visualize, this angle will be 90 degree. Here our coil is in, we can say, YZ plane. This is x axis, this is y axis, this is z axis, and our coil is in YZ plane. Now magnetic field is acting along the y, we can say y direction. So magnetic dipole moment of this coil, which will be perpendicular to its plane, and as its plane is in y and z axis, so its magnetic dipole moment will act along the x axis. So its magnetic dipole moment will be in the x axis. Now this is our, we can say, initial condition. So let's now find out that torque, that about which axis torque will be acting in this configuration. So in this configuration, torque will be m cross b, and we only want to find the direction. So direction of m is in the x, so I, and direction of magnetic field in the z or y, so it will be k. So in this configuration, torque will be acting along the z axis, so we assume that it will take rotation like this. So our coil will be rotating along this axis with this part going here, and this part moving like this. So this will be the basic configuration of the system if magnetic dipole moment aligns along the x-axis. Now this was the initial position, initial configuration, we can say. Now what happens? The coil is initially kept in vertical position and can rotate freely about a horizontal diameter. So horizontal diameter, this diameters, let's mark these diameters also. This is diameter A, this is diameter B. Here B is acting as a horizontal diameter and A is acting as a vertical diameter. So when a uniform field of 4 Tesla is applied along the vertical, it start rotating about its horizontal diameter. So it start rotating about diameter B. The angular speed of the coil coil after rotating by 60 degrees. So after rotating by 60 degrees. Now this is the initial condition. So in the initial condition, we can say we will solve this question by conservation of energy, and total energy will stay the same. So initial potential energy we will find. So initial potential energy will be minus m b into cos of angle between m and b. Now angle between m and b initially, this is m and this is b, both are initially perpendicular, so cos of 90, and this give us 0. Cos of 90 is 0. So this is initial potential energy. Now what happens, that this coil rotates by 60 degree. Now if this coil rotates about by 60 degree, so let me try to show you the rotation. So suppose I rotate it. Here it is. Okay, axes are also getting rotated. Let me choose only this part. Now I rotate this coil by 60 degree. Now suppose now this is rotated by 60 degree. Now what happens? Let us draw some things. This was the original direction of the M. This was initial direction of the magnetic dipole moment, and now it is rotated by 60 degree. So this angle between new M, which is M dash, and old M is 60 degree. Direction of magnetic field is as it is. So here magnetic field is something like this. Magnetic field is something like this. This is P. So now if we find the final potential energy, we have to find minus M cross B into cos of angle between M and B. And now angle between M and B is this one. And as we know that this angle is 60, so this angle will also be 60. So this angle will be 30 degree here. So final potential energy will be M minus MB cos of 30. And as it is rotating, so in the final configuration, it will also have the rotational kinetic energy. So total final energy, can say total energy, that is total final energy will be final potential energy plus final, we can say, kinetic energy. And final potential energy is minus mb cos 30 is 3 by 2 plus half I omega square. And initially disk was at the equilibrium position, so kinetic energy was 0. So we can say total initial energy was potential energy, that was 0, plus kinetic energy, that was 0. So total initial kinetic energy, total energy was also 0. Now total initial energy should be equal to the total final energy, and equating both of these, we will get 0 is equal to minus mb root 3 by 2 plus half I omega square. And from this, half I omega square is equal to mb of root 3 by 2 to get cancelled. And from here we can say omega square is equal to mb root 3 by I, and omega will be under root of all these. So now let's put the value of magnetic dipole moment, magnetic field and moment of inertia. So moment of inertia 0.8, 20 and 4. So this is 20, this is 4, this will stay as it is, and this is 0.8. And solving all of this, we get our answer equal to 13.15 radian per second. And now if we match it, then our nearest possible answer that we can have from all of these options, that is option A. So either none of these are correct, and if you want to find the nearest possible, then it will be option A, 10 radians per second. Now let's move to the next question. So two magnetic dipoles X and Y placed at a separation D, their axis perpendicular to each other, the dipole moment of Y is twice the dipole moment of that of X. So that is 2m and it's m. A particle of charge Q is passing through their midpoint P at angle 45 degree with the horizontal line as shown in the figure. What would be the magnitude of the force on the particle at this distance? So we have to find magnitude of the force. Now, as it is a charge particle, so we know that force on a charge particle is given by Q V cross V. This is the amount of force on it acting on a charge particle when it has some velocity and passing through a magnetic field. Now here velocity is this, so we can say velocity vector is equal to, at the theta is 45, so velocity is equal to V cos 45 or V by root 2 of I plus V by root 2 of J. So it is V by root 2 into I plus J. So this is the value of velocity. Now we have to find out the magnetic field at point P, and then we will take the cross product. So now due to this magnetic field will be, as we know that outside the magnetic field is north to south. So due to this magnetic field direction will be in the positive x direction, and value of magnetic field, we can say value of magnetic field due to magnet x, that will be mu naught by 4 pi, as it this point is axial point for the magnet. So axial magnetic field is twice as compared to the equatorial. So here we will get twice of m divided by the cube of the distance, and as point P is the midpoint, so this will be d by 2 cube, and direction is I. So it will give us d by 2 cube will be 8, and we will get 16 here. 16 into by 4 is 4. So it is 4 mu naught m divided by pi d cube of I. Now for this magnet Y, as point P for magnet Y is equatorial point, so here we will have magnetic field mu naught by 4 pi, half of the magnetic dipole moment. Oh, sorry, as same value of the magnetic dipole moment. In case of axial point, it gets doubled. So for this magnetic dipole moment is 2m and divided by the cube of the distance. And for here, direction of the magnetic field will be along the y-axis, and that we can also get that idea regarding that outside of the magnetic field lines will be in the from the north to south pole. So here magnetic field lines will emerge like this. They will pass through point P and then come halt at point S. So magnetic field will look like this, and at point P, magnetic field will be in the y direction due to this magnet. So it will be in the J. So again formula is same, just direction is different. So 4 mu node m by pi d cube of J, and total magnetic field will be 4 mu node m by pi d cube into I plus J. So if we can see the direction in cross product, if we have same direction, then answer is 0. Here direction of velocity is I vector plus j vector, and here direction of magnetic field is also I vector plus j vector. So their cross product will give us 0, or we can say magnetic force will be 0 here, or option B will be the right answer. Moving to the next one. A magnet of total magnetic moment 10 raised to power minus 2 I ampere meter square is placed in a time varying magnetic field B I cos omega t. Here I represents the direction. So we can say M is 10 of I, 10 raised to power minus 2 of I. And magnetic field is B cos omega t, where B is 1. So we can say 1 cos omega t, and omega is also mentioned. And that is also in the I. And omega is 0.125. The work done for reversing the direction of the magnetic moment at t is equal to 1 second. So we have at t is equal to 1 second, we have to reverse the direction of the magnetic moment. For that, first of all, we have to find magnetic moment at t is equal to 1. So at t is equal to 1, value of m is constant but b is variable. So b will be 1 of cos omega, that is 125 by 1000, into t is equal to 1, that is again 1. So it is equal to cos of 125 by 1000, and we can write it like 5 by 40, or 5 by 40, that will be 1 by 8. Yes, 1 by 8. So cos of 1 by 8. So this is the value of magnetic field at t is equal to 1. Now, if we have to reverse its direction, means suppose at t is equal to 1, our m is this. This is the value of m, and here magnetic field is also pointing in the direction of in the I or in the x direction. So again, magnetic field is also in the same direction. So in this configuration at t is equal to 1, this system will have some potential energy, and that potential energy will be minus of mb cos of the angle, and this is the angle between these two, and angle between these two is 0. Don't confuse with this cos. This is the magnitude of the magnetic field in terms of cos, and this is the angle between magnetic field and magnetic dipole moment. And as mentioned in the statement, that both are in the x direction, so initial angle is 0. So it will be minus mb. We have the value of m, we have the value of magnetic field at t is equal to 1. So let's subscript here 1, so that we remember. Now we have to reverse the direction of the magnetic dipole moment. So if we have to reverse the direction, then what will happen? Then m will be reversed by 180 degrees. So m will point like this in the negative x direction, and b will be still pointing in the positive x direction. So after reversal, that was our initial potential energy. Our final potential energy comes out to be minus mb, and time is same. Again, time is same. It is t is equal to 1 second. So value of b will stay the same. And now angle between both of these two is 180 degree. So final potential energy is positive mb, because cos 180 is minus 1 minus minus plus. So the amount of work done that needs to be done, it will be work done. P final minus P initial, that will be MB minus MB, so 2 MB. So twice value of M is 10 raised to power minus 2, and value of magnetic field is cos of 1 by 8. So cos of 1 by 8, and after solving this we get 0.019, and that is nearest to, we can say, option D. So let's move to the next one. A magnetic dipole is in the constant magnetic field. So it has a constant magnetic field, and we know for a dipole, torque is given by M cross B. Potential energy is given by minus M dot B, and force on the dipole is given by M dV by, you can say, dr. So let's come to the options. Maximum potential energy when torque is maximum. Now when torque is maximum, so torque is maximum at theta is equal to 90 degree, and when theta is 90 degree, potential energy is 0. So when potential energy, when torque is maximum, potential energy is 0. It is not minimum, but it is 0 and neither maximum. So A is cancelled. Zero potential energy when torque is minimum. When torque is minimum, theta is 0, and when theta is 0, potential energy is minimum. So when torque is 0, potential energy is minimum, not 0. Option B is cancelled. Zero potential energy when torque is maximum, that is the case which we solved here. So C is right. Minimum potential energy when torque is maximum. So when torque is maximum, potential energy is 0, and minimum potential energy for this dipole system is negative PE. So again, D is also wrong here. So with this, we end this video here. Hopefully, whatever we have covered up to question number 5. You find all of those helpful and informative in some way. Again, if these videos are helpful to you, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, again, thanks for watching, and we will meet in next video.